today we will take up a slightly different problem. Till yesterday we were looking at the fundamental Graetz problem. The fundamental Graetz problem simply looks at only a slug velocity profile, and then you look at the thermally developing region and calculate the solution for the temperature as well as for the Nusselt number, and finally for the asymptotic case where your x goes to large values, you can recover your Nusselt number for the thermally fully developed region. Okay. So the Graetz profile originally which was done, the Graetz solution done by Graetz himself was a simplistic case, and it was actually 1954 when three people, Sellars and Tribus, I think I have uploaded the solution from original report from 1954 on the Moodle. You can just have a look at it. So these three people, Sellars et al, have extended the original Graetz problem to other cases. So the most obvious case will be to look at a parabolic profile, okay, rather than a plug flow, which was a simplistic case, and do the same solution with a constant wall temperature boundary condition. Okay, so that is the first extension they did, and also they extended it to other boundary conditions like uniform wall flux, and also a case where the wall temperature is linearly varying. Okay, so these are some extensions of Graetz problem. So we will try to do a couple of these extensions. The first extension that we will do today is for the parabolic velocity profile. So I will call this as Graetz solution extended for parabolic velocity profile. Now obviously when the Graetz solution was extended, the original Graetz solution for a plug flow was having Bessel functions as the eigenfunctions, and once the extension was done, it was observed that the solution was not as simple as just getting a Bessel function. Okay, so we will look at the nature of the eigenfunction, how it looks, and these eigenfunctions have to be estimated in some way or the other. That's when Sellars did it, they didn't have access to computers in 1954, so they tried to do a kind of mix and match approach. So they split the problem solution into three parts, one for small values of r, one for middle values of r, one for large values of r. They got three different asymptotic cases and they had patched up these solutions. Okay, but nowadays you can solve the ordinary differential equation numerically directly to get the eigen functions. Okay, so anyway, so the thing is the solution to the eigen functions are not as straightforward as what we saw in the original Graetz problem. So now we know the energy equation, so we will write down the energy equation still remains the same, there is no change, 1 by r d by dr r dt dr. Okay, so this is the form of the energy equation will be still working. We will neglect the axial conduction with respect to the radial conduction, and still you have the convection term due to the axial velocity. So we assume that there is no radial velocity and no variation in the theta direction. Now the question is, earlier we just assumed u to be a constant and just substituted as some um. Now we have to put the actual parabolic velocity profile coming from the fully developed, hydrodynamically fully developed case. To do that, first you can also do this in a dimensional form like what we did for the Graetz problem. You can substitute for u in terms of um and leave everything in a dimensional form, and then you can proceed to a solution, but it will also be a little bit simpler to do it in non-dimensional form. So we are going to introduce some non-dimensional variables in the beginning and then substitute those non-dimensional variables. So I will introduce for temperature theta like the way I introduced before, it is T minus T wall by T inlet minus T wall, so that at x is equal to 0 you have theta equal to 1 and r equal to r naught, your theta will be 0. Okay, and at r equal to 0 your theta should be finite. So these are the boundary conditions for theta defined this way. And we will also introduce a non-dimensional radial coordinate. We will use the symbol eta, so that will be r by r naught, that is the radius of the duct. Okay. And we will introduce another non-dimensional coordinate for the axial location or axial coordinate. So we will use the symbol zeta for that, and we will define this as x by r naught by Peclet number. So this is the non-dimensional axial coordinate, this is the non-dimensional radial coordinate eta. Okay, the way that we have defined this x by r naught by Peclet number, okay, this is convenient because once you get the solution for variation in the x, you saw that in the Graetz problem you had a exponential minus, you had something like x by d naught by Peclet number, right. So in order to accommodate this variation and group this together in one non-dimensional form, it is convenient to define this entire group as, so this group appears together. Okay, you do not find x separately, d separately and Peclet number, they all come as one single group for variation along x. So therefore it is wise to define a non-dimensional variable zeta grouping this together. Okay, now there is another non-dimensional number named after Graetz, okay, it is called the Graetz number, and actually 1 over Graetz number is defined as basically x by d by Peclet number. So this is basically how the Graetz number is defined. So this particular non-dimensional grouping of x by d by Peclet number is referred to as Graetz number inverse. Okay. So it basically tells you about the non-dimensional axial variation is represented by this non-dimensional number called the Graetz number inverse, and therefore you can see that if I define x by r naught by p as one non-dimensional group, so this is nothing but a function of Graetz number. Okay, so this comes out as Graetz number by 2 exactly. Okay, so this is a one form of convenient form of grouping. So, okay, so we will stick to this particular non-dimensional formulation for eta, zeta and theta, and therefore we will substitute this and we will see how the governing equation reduces to. We will also use the parabolic velocity profile. So basically that is u by um is equal to twice 1 minus r by r naught the whole square. Okay, so in terms of non-dimensional radial coordinate, that is 1 minus eta square. Okay, so x from here, this will be, already you know Peclet number is what, this is rho um or d by alpha. Okay, so d or d naught you can use, this is the diameter of the duct. So therefore we can express x in terms of zeta, so this is d naught by alpha into zeta. Okay, so you have into r naught, which I will write it as d naught by 2, so you have a term something like this. Okay, or I can express everything in terms of r, so I can write this as 4 r naught square, so this becomes 2 r naught square. Okay, so this is the transformation I have to do from, I have to substitute for x from this expression, so it becomes in terms of zeta, and for r I can use this transformation so that I can substitute in terms of eta. Okay, so if you do that, so you will be ending up with, for u you have already 2 into 1 minus eta square. If you substitute the non-dimensional variables, let me call this as equation number 1, the energy equation. So divided by alpha into dt by dx. So t in terms of theta, that is basically Ti minus T wall d theta by, now once again x we can write in terms of zeta from here, okay. So this will be d zeta, and you have the other terms, you have 2 um r naught square, and there is an alpha coming in the numerator, okay. So that should be equal to, so when you substitute for r in terms of eta, so the r naught cancels between these two, and then you have an r naught square coming here, okay. So you have 1 by r naught square, okay, d by d eta into eta d. So I substitute once again in terms of theta, so this becomes d theta by d eta, and then I have Ti minus T wall, okay. The reason why I use this theta here, because my inlet temperature is a constant, wall temperature is a constant, okay. So it is not a function of either x or eta. So for the case of constant wall temperature boundary condition, if you non-dimensionalize this way, so my Ti minus T eta will come out of all these derivatives and get cancelled on both sides, okay. So therefore this cancels off, you have r naught square which cancels off here, you have alpha which cancels off, and then 2 cancels off right away. So finally you are left with a expression 1 minus eta square into d theta by d zeta, which is equal to whatever is there on the right hand side, okay, 1 by okay, I have left 1 by r, so that should be 1 by eta here, 1 by eta d by d eta d theta by d eta. Okay, let me call this as equation number 2. So therefore this is the non-dimensional form of the energy equation after I substitute for the fully developed velocity profile. So this has become a little more compact than when I work with the dimensional form, right. I have so many terms in terms of I have I have alpha, all those things appearing, now all those things are eliminated, okay. So this is a much, so I always recommend that you can, if you like to work with a more compact form, you can define non-dimensional variables in the beginning and then you can use it. For the constant wall flux boundary condition, however, you cannot define a non-dimensional theta like this, because there your wall temperature will be varying and therefore you cannot define, so you have to just say T minus Ti or something like that, okay. So you have to be careful, for the case of constant wall temperature condition you can define a non-dimensional theta, for the case of constant wall flux you cannot do that, okay. So but still you can, for that case also you can define your non-dimensional eta and zeta, okay. That will save some, save some effort in removing all this and variation in alpha and all those terms, okay. So now the boundary conditions for this in terms of theta, to solve this how many boundary conditions we need? 3. So in direction, in zeta direction how many in eta and how many? 1 in zeta and 2 in eta direction, right. So therefore theta now at any value of eta corresponding to zeta equal to 0, so that is basically saying that t at x is equal to 0. So the non-dimensional theta will be 0. What will happen at so if you look at the 1, so if you look at the problem configuration, So this is your region which you are looking now. So this is your delta T, this is your delta, okay, and in fact what you are doing right here, it is not something exactly like this, but you are starting from a point where it is fully developed, that is your coordinate. So you can consider that your thermally fully developed region meets somewhere further down, okay, and this is your coordinate right here, this is your x, this is your r. So once the velocity profile is fully developed, then you start looking at the thermal entry length problem, okay. So you start basically heating from here or maintaining a isothermal condition. So in this particular case, at x is equal to 0, this is where you are calling this as Ti, the temperature which is entering the thermally fully developed region, okay. So at x is equal to 0, theta should be 1 because T should be Ti. And the other boundary conditions with respect to eta. So at eta equal to 0, your d theta by d eta should be 0 or theta should be finite. Both are equivalent boundary conditions, and the remaining boundary condition at r equal to r naught. So that corresponds to eta equal to what? 1. So at any value of zeta at eta equal to 1, what is the boundary condition? 0. Okay. So therefore now you have a partial differential equation like before for the Graetz problem. Only thing you can see, earlier you did not have this 1 minus eta square, that was a constant plug flow case. Now you have this extra term and the other boundary conditions are all same, okay, there is no difference. So now we have to solve this PD. So the same method that we use separation of variables, we will do it here, okay. So how do we start? We say theta of zeta and eta will break up into two parts, one x which is a function of zeta and capital R which is a function of eta. So the actual solution is product of two solutions, one which is, so these are two independent solutions, okay, one function of only x, the other function of R or eta, alright. So therefore if you substitute this into your equation number 2, okay, assume that this is your solution and substitute so you end up getting 1 minus eta square into dx by d zeta and your R is constant. On the other side you have 1 by eta, you have x constant, d by d eta, eta into dr by d eta, okay. So I divide both sides by x into r, so this becomes 1 minus eta square by x into, so I will also take 1 minus eta square on the right hand side, so this becomes 1 by x dx by d zeta, this is equal to 1 by r into 1 minus eta square into, I have already a eta here, into d by d eta into eta dr by d eta, okay. So now I can see that this is a function of zeta, this is a function of eta, so these both have to be equal and therefore they have to be equal to a constant which is always negative, okay. So in order to have an exponentially decaying function along zeta, this has to be a negative constant, okay, and this is the eigenvalue. So now I can write this into form of two ODEs, one where I can say dx by d zeta plus lambda square x equal to 0, I will call this as number 3, and the second ODE I will expand this term right here. If I expand it, I can write this as d square r by d eta square plus 1 by eta dr by d eta plus you have lambda square, and this entire term I am taking it to the other side. So this is 1 minus eta square into r, this is equal to 0. I will call this as my equation 4. So this is the first ODE with respect to x, second ODE with respect to capital R. Okay. So I just expanded this term right here. So this is eta into d square r by d eta square plus dr by d eta into 1. Okay. So that is what I did, and I already have eta at the bottom, so I divide everywhere by eta, and so you have this term lambda square into r into 1 minus eta square. Okay, so therefore I use the same boundary conditions there, and with respect to r, now you can see that you have two homogeneous boundary conditions, because with respect to theta you can substitute as r into x. Okay, since x has to be finite, it cannot be trivial, therefore the boundary condition should apply to r, right. So whatever you say here, so your d theta by dx, so this will be d by d eta into, you have x of zeta into r of eta, so this should be equal to 0 at anyway, so I can write this as eta equal to 0. Okay, so this can be 0 only if I can say dx by d eta, if x is equal to 0 also this can become trivial, but the problem is if x equal to 0 there can be no solution. Okay, therefore this implies that your d by d eta at r d by d eta r at eta equal to 0, this can only be 0. Okay, right, because this can be 0 only if either of these is 0. If x is 0, that means my entire solution becomes trivial. Okay, whereas r at eta equal to 0 can be 0, so that is the only other option. Okay, so therefore this is the boundary condition which falls on r. The other boundary condition, that is theta at zeta eta equal to 1, this is equal to 0, the same way. So once again I can say my x of zeta into r of eta equal to 1 is equal to 0. So once again x cannot be 0, so therefore this indicates my r eta equal to 1 should be 0. So therefore these are the two boundary conditions with respect to, so this will be anyway normal derivative, not the partial one, because r is a function of only eta. So to solve the eigenvalue problem, now you can see that eigenvalue problem has two homogeneous boundary conditions with respect to eta. Okay, so therefore equation number 4 is the eigenvalue problem which I have to solve and apply the boundary condition. Now if you look at equation number 4, what kind of an equation is that? This is where you have to be a little bit careful. You look at the structure of the Bessel equation I have given, it is very deceptive, but if you look at it a little bit more carefully, if you multiply everywhere with eta square, okay, the first 2, the second order and the first order derivatives appear to be similar to the Bessel equation, but the third term here will have lambda square eta square into 1 minus eta square into r. So that structure is not the same as the Bessel equation. Okay, so the Bessel equation has minus some constant term, minus some constant number, minus nu square. Okay, it does not have minus a function of x, right. So therefore this is not the actual Bessel equation. So what we can call this as a general form of any eigenvalue problem, which is called a Sturm-Liouville equation. Anybody has heard about this equation, Sturm-Liouville problem? Anybody has taken partial differential equation course? Anything to do with differential equation? How many have done? Only one? So you must be taught Sturm-Liouville equation, because that is the most fundamental part when you talk about separation of variables. Any general eigenvalue problem, okay, for which you can find the eigenfunctions, it is generally called as a Sturm-Liouville equation. That includes even the Bessel equation. Okay, so this is a generic name given to any eigenvalue problem. That includes all kinds of equations, all kinds of second order ODEs, all kinds of Bessel equations, whichever that you have encountered. Okay, so that is a generic category of Sturm-Liouville problem. So therefore we cannot pinpoint this to any particular familiar equation. Okay, this is not a Bessel equation, but it can be generally called as some Sturm-Liouville equation. Okay, so and I will just give you the generic form of the Sturm-Liouville equation, and you yourself can see that it is generally of this particular form. Okay, where this is the weight function. So any ordinary differential equation which can be cast into this particular form, okay, forms a Sturm-Liouville system of equation, and this includes most of all the eigenvalue problems. Okay, even this equation right here, we can just cast it in this particular form. Okay, so for this case you can put it as minus d by d eta dr by d eta plus 0 equal to lambda square into 1 minus eta square into eta into r. So you just expand and see. So this is eta into d square r by d eta square, okay, plus you have dr by d eta. Okay, so I am multiplying everywhere by eta, okay, plus you have lambda square 1 minus eta square into eta r, right. So I can write that equation in this particular form. So this comes to a Sturm-Liouville kind of an equation. So now if you compare the coefficients, okay, the coefficient here p of x is nothing but eta and q of x is nothing but 0, and of course lambda here is lambda square, okay, and if you look at this weighing function, this is a function of x here, so that this has to be a function of eta. So this entire thing is the weighing function or weight function. Okay. So the property of any eigenfunction, as I said yesterday, it has to be orthogonal, okay, that includes even Bessel functions, and any general eigenfunctions which are of the Sturm-Liouville type have the orthogonal property, and for the Sturm-Liouville kind of equation set, the orthogonal property will be, you have integral a to b y of n into x y of m into x into w of x dx, okay, is equal to delta mn. So this is the orthogonality. Okay. So what it says, when m is not equal to n, this Kronecker delta, this will be 0, right. When m is not equal to n, this will be 0. Therefore they have to be orthogonal, means if m equal to n, then only this will be equal to 1. So in that case this will be yn square into the weight function dx integral should be equal to 1. If m is not equal to n, this integral will be equal to 0, just like what we saw yesterday. If you multiply Bessel function jn x into jm y, okay, if m is not equal to n, so they will be 0, the integral product will be 0. Okay. So this is the principle of orthogonality for any Sturm Liouville problem. So here you have identified what is the weight function, correct. So in this particular case, what should be the orthogonality condition? So if I integrate, what should be the limits of the integral? 0 to 1, good, and then instead of y I have my rn of eta into rm of eta, and what is the weighing function here? Eta into 1 minus eta square into d eta. This is nothing but your Kronecker delta. This is the delta function. I hope all of you know what a delta function is. So it is equal to 1 at only one value, everywhere else it is 0. So for the case where your m equal to n, then this is equal to 1, otherwise it is 0. Okay. So therefore this is my orthogonality condition which I will use. Where should I use the orthogonality condition? When I solve the ODE, when I want to calculate one of the constants, right. So this I keep it now. So therefore you see that the solution to the Sturm Liouville problems can be represented as, so you can say in this case that you can write this as summation of some Cn times Rn of eta, where n can go from 0 to infinity. So once you know the eigen function, okay, so you can write this solution for theta or whatever you call, you can write this as r prime or whatever. So your r of eta can be written as the eigen function times the constant summed over all the values of eigenvalues. Okay. Now the question is how to basically find the eigenvalues. So for that we have to, it is not as simple as solving the Bessel equation, because now this is a general Sturm Liouville problem and you have to solve the ordinary differential equation, that is equation number 4, we have to solve this numerically. Okay. You cannot, this is not a generic, this is not a particular form of any equation where you can get a ready-made solution. Okay. So any general Sturm Liouville problem, if it is familiar equation, then you can get a solution straight away like the Bessel equation. If it is unfamiliar, then you have to apply these boundary conditions, two boundary conditions, and you have to solve for the eigen functions which are in terms of r. Okay. So therefore this is a little bit rigorous procedure, you know, I am not asking you to do it. However, this sellers, they have done it in a slightly different way, they use some approximate methods to patch it up. I do not think that is a very good technique right now, because we have access to computers and you can solve this equation straight away numerical. Now the question is, for solving this you need the eigenvalue, okay. So that becomes like a constraint, and the eigenvalue can be related to the derivative of R, okay. I am not going into the detail, but there is something called as a Rayleigh coefficient, okay, for Sturm-Liouville problems, so which relates your eigenvalue to the derivatives of R, and therefore you can guess the value of lambda, right, just like your shooting method, you guess your value of lambda and then you apply the boundary conditions, okay, and then keep marching until the other boundary condition is satisfied, and then again you use that derivative and then check if your lambda is correct, okay. So this has to be done iteratively till you guess the right value of lambda, okay. So overall what I would like to say is that you have to solve equation 4 numerically to obtain the eigenvalues and the eigenfunction. So the eigenfunction is basically R, variation of R with respect to eta. So once you do that, so now your final solution so can be expressed now directly as theta, which is a function of zeta and eta. Now what is the solution to this equation number 3? This is a straightforward ODE, x equal to some constant c e power minus lambda square x, okay. So that is a straightforward solution. So therefore your final solution theta will be product of x and r, okay. So as I said, you can have multiple values of eigenvalues, and for each of this you will have a solution, okay, eigenfunction. So therefore you have to linearly superpose all these multiple solutions, so therefore you use a summation from n equal to 0 to infinity, and the constants coming from this c and here you just club them together as 1c into the eigenfunction coming out of that is Rn of eta, and the solution which is coming out of this, so this is basically zeta here, that is e power minus lambda square zeta. This is your form of your solution, right, the product of this and this, okay. So now the thing is finally, so now you have to do it numerically to solve for the eigenvalue and the eigenfunction. The remaining constant c can be solved by applying what? Yeah, we make use of the orthogonality property, but we have to use the remaining condition for theta, okay, that is theta at zeta equal to 0, which is 1, okay. So that is nothing but summation n equal to 0 to infinity Cn Rn of eta, and for zeta equal to 0 that becomes 1, okay. So now to get Cn out of this I make use of the orthogonality condition, so I multiply both sides by the weighing function times some Rm of eta, okay, both sides, and integrate it. So from 0 to 1, so the weighing function is eta into 1 minus eta square into some Rm of eta into d eta, okay. I multiply this from both sides, so I have integral 0 to 1 summation eta equal to n equal to 0 to infinity eta into 1 minus eta square, I have Rm of eta Rn of eta into Cn, so Cn will be here into d eta, right. So now you can see that based on the orthogonality property, if m is not equal to n, then this entire thing will be 0, okay. Only for m equal to n this will be 1, okay. So therefore we can say this is integral 0 to 1, there won't be any summation, because for any value of n which is not equal to m, the summation will be anyway leading to 0. So this will be Cn into eta into 1 minus eta square into Rn square d eta. So if I say 0 to 1, eta into 1 minus eta square into Rn square of eta d eta will be actually minus 1 by, this is the actual value. If you know the eigen function, you have to take the derivative with respect to eta, and this will be at eta equal to 1, and this is the value of this complete product and integral, okay. So this is the property. So this is also a property of the Sturm-Liouville system of equations. So therefore you can calculate your C so your Cn comes out as integral 0 to 1 eta into 1 minus eta square into Rn of eta d eta divided by, so the summation is gone, you have integral 0 to 1 into eta into 1 minus eta square into Rn square of eta d eta, right. For m equal to n, so this becomes Rn square, otherwise this is 0. So basically we will stop with the fact that you can calculate your Cn here. I will give you the actual calculation of these integrals, two of them. I have to check whether this is with respect to eta or whether this is with respect to lambda. So let me just hold on for that in the next class. So I will give you the expressions for evaluating these two integrals, and then from there it is mere substitution, okay. So once you get your constant Cn, so therefore your solution, so for theta is known once you know your eigen functions and your eigen values, okay. So these people Sellars et al, they have, with some approximate method, they have evaluated the values of eigen values and the corresponding constants. I will give those tables also in the next class when we do the solution, and from there you can asymptotically reach the case of large values of x, and you can recover your earlier result for Nusselt number, that was some 3.6 for constant wall temperature with a parabolic profile. So you can exactly reach that asymptotic value. So in the next class on Tuesday we will complete this solution, and so we will look at very briefly the extension of the Graetz problem to uniform wall flux boundary condition. There I have posted already in the Moodle a solution for channel flow, where I assume a plug flow velocity distribution and a constant wall flux boundary condition, and I have posted the form of solution. I'll explain very briefly how to do it, and you can look at that solution and you can very easily understand it. For the case of constant wall flux boundary condition, you have to tweak in such a way that the eigenvalue problem has homogeneous boundary conditions, whereas if you have a constant wall flux boundary condition, that is not homogeneous, okay. So therefore we play around with the solution in such a way you reach a homogeneous boundary condition, and that is explained in the derivation which I posted on Moodle, and you can do a similar kind of a derivation for the duct flow. So what I have done is for a channel flow, a very similar procedure for duct flow can be done. So that will be a extension which will be useful to you, and that we will go towards the integral solution, the approximate solutions to internal flow problems, okay. It's very similar to your external flow integral method, okay. That will be the last topic, and with that we will wrap the internal flows, laminar internal flows, okay.